So hello everyone, welcome to the class Calculus Grade 12, and today we're going to practice problem solving for units 4.1 to 4.3, in which we covered advanced techniques of curve sketching. In this classes, you and me guys discovered new properties of functions such as critical points, local minima, maxima, local extrema, increasing interval and decreasing or certain irregular functions shapes like cusps or vertical asymptotes or horizontal asymptotes. Do you recall anything of that?
Yeah.
So today we're going to structure all of that information down bit by bit, and we're gonna start with simple problem solving, and we're gonna of course start from unit 4.1, and depends on the time frame, how would we deal with these problems, how many we can cover for today. But anyway, we're gonna start with the simplest one, and it's dedicated to increasing and decreasing functions. So Yusuf,
Yeah.
could you be so kind and please explain me what do we mean by saying that function is increasing or decreasing on an interval? What in the mathematical language, what are we describing in this matter?
We can say that wait, so describe I'm not sure to exactly explain it. Like
So let's say it in other words. So the property that we're giving to the graph in a certain interval is that it's increasing or decreasing, right? So let me sketch the axis right here real quick. Can you see it on your screen?
yeah.
And let's say my function looks like this. And what I actually study about this function, I study value of points that belong to this curve, right? I want to know its y value and its x value. And what else can I do? I can move to the left or to the right by changing the x value, right?
Yeah.
That's my variable. That's how I slide it along the curve. And if I slide to the right, it means I'm going forward along the curve. That's usually taking us positive direction. And I have another point after a certain value x, right? Delta x. And this point has another y value, right? It would be
Yeah.
different x value. So let's say this first point was x1 and the second point would be x2. This would be y1 and y2 correspondingly. Does it make sense?
Yeah.
So now we can say we can see that x1 is less than x2. Is it true?
Yeah.
And another statement that we can make that y2 is greater than y1, right?
Yeah.
Or we can say that y1 is less than y2. So another pattern that we see here, that our function increasing when moving from first point to the second one, right?
Yeah.
This direction. Because y2 is greater than y1. Direction we know from this symbol. If x2 is less than x1, it means we're going to the left, right?
Yeah.
Basically. So now we see that y1 is less than y2, so we make a statement that on interval from x1 to x2, function is increasing. Am I right?
Yeah.
So that's what it means. That if I say that function is increasing, I say that value of y is increasing as I increase x coordinate.
Yeah.
But the other way around, if I increase x coordinate, but my function of value decreases, what if y2, what if my function was like mirror image of this one like this? Then here and here, if I take x value, right? x1 was here, and x2 is gonna be lower than y1 in this case. Do you see this?
Yeah.
If it's the other way around. In this case, y2 is less than y1, so my function is decreasing. That's what we're trying to highlight when saying function decreasing or increasing on an interval, because it's basically gives us the shape of a curve, right? Right? Direction. Yusuf?
Yeah.
So now tell me in your words, what is it that function is decreasing or increasing on interval?
So the question is, what is
Well,
decreasing?
well, yes, what is decreasing and increasing function on interval? What is the relation between the name and basically phenomenon that happening with the function?
Okay, so an interval is increasing if the function values within the interval are increasing.
No, interval is not increasing. The value of function increasing.
The value of function, yeah, the value of function is increasing.
Function f is decreasing, you see?
Yeah,
Function f is decreasing. Function f is increasing, not the interval.
yeah, and if the interval is decreasing, if the interval is decreasing, if the function values within the interval are decreasing, if as you move to the left and to the right of the graph.
So you
So
can
the
also
increasing and
say,
decreasing, basically like
can you read this in the notation?
which one, sorry?
Right, the one right here. Well, let me show you. This one. Can you read it?
Yeah, so fx1 is bigger.
F of x1.
F of x1 is bigger than f of x2.
F of x1 less than f
Less
of
than,
x2.
sorry, f of x2. Yeah,
So when f of x1 less than f of x2, it means function is increasing.
yeah,
And when f of x1 is greater than f of x2, it means function that is
is decreasing. Yeah.
decreasing. So that's how you can simply explain it in 2 lines.
Yeah, and like the term increasing and decreasing refer to the uh direction of change in the function values.
Yeah, and we
As you move,
always mention that from x1 to x2, we're always walking to the right,
yeah,
because x1 is always less than x2, because that's how we determine whether function increasing or decreasing. Because if we say that x2 is less than x1,
yeah,
it means we're moving the other way, the other
yeah.
direction.
So they're used to describe the behavior of the function within a certain interval.
Perfect. Great explanation, Alan. Oh, sorry, Yusuf. And now I was already thinking about Alan, who's gonna help us with this portion.
Okay.
So can you explain me how sign of the derivative is connected with statement whether function increasing or decreasing?
Okay.
How derivative is part of this party?
Well, it's the slope the slope is negative, you would know it's a decreasing function, or the interval is x1 is less than x2. But if it's positive, then you know the function is increasing because the interval would be x1 is less than x2. Sorry, if it's decreasing, it's x1 is greater than x2 if it's decreasing, and if it's increasing, it's x1 is less than x2. So
Beautiful.
it's
Mhm.
based off the slope. If the derivative is negative, the slope is decreasing, or other way around. Sorry. If the slope is negative, the function is decreasing.
Oh, yes. Or another way around, we can say that if function is increasing on an interval, derivative would have negative value at every point of this interval.
Okay, that's a
Does
simpler.
it make sense? Does it make sense?
Yeah, it's better than what I said.
It doesn't matter. It's not. It's just different.
Yeah.
So, is there any questions about this topic? Can we move on to the problems?
Yeah.
Yeah.
Yusuf?
We can move on. Yeah.
Perfect. So, let's take a look at this simple equations. And right here we ask, determine the points at which derivative equals 0 for each of the following functions. So let's pick one. Which one you like? Let's pick this one with fraction,
Okay.
where we have basically a coefficient rule, right?
Yeah.
So let's take a look into D. So we need to find the derivative of function. First of all, if we would like to know point at which derivative equals 0, first we need to find the equation of the derivative, right? To
Yeah.
do so, we would differentiate the 5x over x squared plus 1. And I would apply coefficient rule first of all. And that's it, I think. So let me remind you how it looks like. So we have function that looks like f of x over g of x. And we differentiate it. It would be equal to f differentiated of x times gx. Subtract f of x times g prime of x over g square over x of x. Am I right?
Yeah.
Or is this the other way around? Or is the derivative on the right spot?
No, derivative is in the right spot. Yeah.
Perfect. So now let's apply this function. Now it's much easier when you see it, right? You just need to write it down 10 times, and 11th time you're just going to remember it. So derivative of f of x is going to be 5 times x squared plus 1. Subtract f of x, which is 5x, times derivative of this, x squared plus 1. As soon as we don't, it's not a composite function, right? We don't have inside and outside coefficients. So we're simply going to factorize it as a product of two terms.
Sorry, can I ask, what did you what is all this up here? Like here, here, and then like this.
Well, explain how you would determine when the function is increasing
No,
or
no, no,
decreasing.
not that question. Like the equal signs here, and like that equals this. Like 5x, the derivative of that, and what's like
Yeah, and what about it?
like I don't understand it.
Equal? It means
Oh, like
left and right hand side is equivalent.
why did we write it?
And here,
Why did we write all this?
so stay focused. We're looking for derivative of an equation.
Yeah.
Read the question. Determine the points at which derivative f prime of x equals 0 for each of the following functions. We picked function d,
Yeah.
and now we're looking for derivative of function d. If you look right here, it's f prime of x, which is 5x over x squared plus 1. It's exactly equation from example D, and we would like to differentiate it. So next step, I'll write equal, and I have feature brackets. There, it basically it means part of my solutions, but here I'm breaking down this equation into coefficient formula for you to explain you how to differentiate when we have function divided by function. So this is the formula that we gotta use for differentiation.
Yeah.
F of x is 5 times x. G of x is x squared plus 1. So now I differentiate it using this formula, where nominator is derivative of f of x times gx, subtract f of x, times g prime of x.
Okay.
Is it clear now?
Yeah.
Sorry guys if I'm confusing you. So do you understand how I got this part?
Yeah.
Yeah.
Now I have f of x, which is 5x, derivative of g of prime of x. It's x squared plus 1. I just treat it as simple derivative of a sum, right?
Yeah.
Derivative of several terms. And here I have coefficient, which is 1, or constant, right? It's not a variable. It's just a number. And x squared. And if I differentiate it, I get 2x. So I will write 5x times 2x. All of this over x squared plus 1 squared. Am I right?
Yep.
Yeah.
So now let's go ahead and open the brackets. We're going to have 5x squared plus 5, subtract 10x squared over x squared plus 1 squared. Now, next step, we're going to have 5 subtract 5x squared. Am I right? For the denominator. Over x squared plus 1 squared. So we gotta find for what value this function equals 0. This is basically our derivative. We were looking for the equation of the derivative. We don't need to simplify it.
Yeah.
No reason. Unless we were asked to. So here, first thing first, I can see that this function can be equal to 0 if and only if the denominator equals 0, right?
Yeah.
And denominator doesn't equal 0. That's two important rules, because you can just say that denominator equals 0, then yes, okay, this equals 0. If your denominator also equals 0, you're gonna have problem when 0 divided by 0. Am I right?
Yeah.
Which gives us value of a derivative like infinite corner or infinite angle. We don't know which direction it looks. So we say that function is not defined at this point. Am I right?
Yeah.
So, but here we are lucky, and I can see the denominator here never ever equals 0, because I have x squared plus 1. And what is x squared? X squared is always positive number or 0.
Yeah.
And here I have a constant which is greater than 0 and positive. So no, and this is squared one more time. No way it's going to be negative or 0.
Mm-hmm.
So I'm only looking for solutions for the top part. So now I forget about the denominator and I just simply go ahead and look into the denominator, 5 subtract 5x squared. And I need to find when this is equal to 0. What is the value of x? And I would simply do what, guys?
Can't you simplify a 5?
Yeah.
Yeah, we can simplify it by 5 and we're gonna get 1 subtract x squared equals 0.
One. Oh, sorry. Yeah, 0.
So I say that x squared equals 1. So x equals 1
Oh,
Yeah.
yeah.
or -1.
Oh, yeah, yeah.
But you gotta be careful because what is x? X is square root of 1.
Yeah.
Yeah.
But can
Plus or minus.
can the square root be negative? Can the square of a number be negative?
Yeah.
No,
Yeah.
no, guys.
Why
Hmm.
not?
Yeah, you're right.
Is it or is it? Sorry, I'm tricking you. When we multiply a negative number by itself, we're getting a 1, for example. -1 times -1 would be 1. So if we take a square root of 1, we can get either positive or negative number, right?
Yeah.
Well, now that's clear. But other way around, you cannot find the square root of negative number
Yeah.
unless you're working with complex numbers. And that's what is not my part of your education, complex numbers. It's good luck with your future professors. But today, in our example, we have square root of 1, right? X equals square root of 1 because x squared equals 1. So we have two solutions when x equals 1 and -1.
Oh, okay. Yeah.
So we say that, let me highlight it in the middle of summarizing everything we did here. So it's you gotta look at it in lines because everything is in order here, right?
Yeah.
And result of all of it is that f prime of x equals 0 for x equals 1 and -1.
Yeah.
And that's was the question. Determine when derivative equals 0.
I have a question.
Yes.
How would the points at which fx equals 0 for the function change? Like if hmm, the
So
numerator
sorry, f prime of x or f of x?
f of x,
So
not prime.
f of x
Yeah.
equals 0.
Yeah. Change if the numerator was like a different constant. For example, like 3 instead of 5. Would there be like additional points at which f of x equals 0? Or will it be still be?
If the coefficient in the denominator was different.
Yeah.
So as you see, if we have single term with any coefficient in this case,
Yeah.
and we perform such an operations, eventually we were lucky to simplify it
Yeah.
in this
Yeah. You
case.
said you were like,
But in another case, let's say if we didn't simplify it, right? Let's say we take some arbitrary number instead of 5. Okay?
yeah.
So let's say if we ended up with something like a and b, a subtract bx squared,
Yeah.
then you would simply move a to the right hand side with negative sign, right?
Yeah.
So it's gonna be a negative. We cross it out from here, and we have negative b x squared equals negative a. Now
Yeah.
we simplify the minus, and now we divide by b because it's factor. So we're
Yeah.
gonna divide by b, and now we're left with x
X
squared
squared.
equals a over b.
Yeah.
And now we simply taking a root of this and we have x. It would be
Oh, okay, yeah.
exactly the same stuff when we're still gonna have only 2 points
Still 2 points, yeah.
if we're working with the same power functions. If we would have function of third power here or 5x squared, we
Oh,
would
okay.
have polynomial function of another power, which leaves us with more roots,
More
more
roots, yeah.
solutions for 0.
Yeah. Okay, sounds good.
Any questions, guys? How you? I kind of like it so far. Did you copy this solution into your copybooks?
Yeah.
So the answer is f x equals 1 and -1 when f of x equals 0, or f prime of x equals 0.
No, f prime of x equals 0 when x equals 1 and -1.
Okay.
So point, yeah, this is not the final answer. You see, we gotta read carefully. They say determine the points at which f prime of x equals 0. So we know only one coordinate now. We only know x of these points. And now we need to find the y value. And how do we find it? We simply stick this x value into the function.
Sure.
So we're gonna have two solutions, f(0x1) and f(0x2), right?
Yeah.
In first case, it's gonna be 5/1 + 1. And in another case, when it's negative, it's gonna be -5/1 + 1 again.
Yeah.
So it would be 2.5 and -2.5. So my 2 points, let's say D and C, right? D is gonna have coordinates of 1, 2.5, and C is gonna have coordinates of -1, -2.5.
So are we supposed to plug it into the original equation or but the derivative equation?
Yes, we're supposed to plug it into original equation because we're asked determine the points at which derivative equals 0 for each of the following functions. So what is the coordinate of the function where derivative of this function equals 0? So because if you plot these two functions, if you plot the function of the derivative and initial function, x value is the same, it's corresponding, but x value is different, or y value is different.
Okay.
Y of the function in this point is equal to -2.5 in point at x equals -1, but derivative has y equals 0. So f prime of x equals 0 and f of x equals -2.5. F prime of x equals 0 and f of x equals 2.5. Is it clear?
Yeah.
Really? Now it's clear?
Yeah.
So f prime of x and f of x. We call them, they're both y coordinate, right? Because f prime of x, it's the same function as f of x, just differentiated. It's not different. It's not some function from another dimension. It's same. It's same function with variable and dependent value, right?
Yeah.
And we just call them y and x. So did you copy this? Can we move on?
Yeah, I got it down.
Perfect. Well, actually, let me screenshot it. It looks kind of nice. Don't you think so?
Yeah.
So I'm clearing the drawings. And do you feel like you would like to solve one more of these?
If the square root one.
Yeah, the square root one.
This one?
Yeah.
Okay. And let's make the second step for D, and then we're going to move on to B, okay? So second step for D. Explain how you would determine when a function is increasing or decreasing. So knowing all that, all these coordinates of a point, how, and knowing that derivative at this point equals 0, right? How would you determine when the function is increasing or decreasing?
The sign.
So when derivative equals 0, it means it's critical point, right?
Yeah.
So we gotta, to determine whether function increasing or decreasing, we gotta take a look at the values of function before and after this point. Am I right?
Yeah.
So what would you do? And if you take a look at the point here and here, you already know the relations between the minimum or maximum point and points near it. Remember how we did it in class? We compared the value of function in this point and here, and if this is less than this, it means function is basically decreasing because we're looking from left to right. And if in this critical point value is less than in point after, it means function is increasing in this interval. Basically what Yusuf told us, right? F of x1 less than f of x2. So function is increasing.
Yeah.
So how would you determine when function is increasing or decreasing for this example D?
Hmm. So wait, so if you could look at the sign of it though, can you not? Because you know that so x2 is greater than x1. Wait.
So you're saying that you would use first derivative test, right? Do you recall it? What is the first derivative test?
No.
No, guys, don't disappoint me. First derivative test is the test for the derivative sign around critical points, remember? First derivative test consists of two parts, and that's why we're doing this exercise. It simply breaks the first derivative test in two pieces. You are defining critical points when derivative equals 0, thus it's gonna change sign, all right? Or it won't if the sign of the derivative is constant, right? But that's what we want to see. We find these critical points, we take two values to the left and right, and we look at a sign of the derivative. If the derivative is positive, it means function is growing. If derivative is negative, it means function is decreasing.
Okay.
So we already know the equation for the derivative, right?
Yeah.
1 minus x squared. Oh no, it's 5 minus 5x squared over x squared plus 1. But one thing you need to mention here, this is never negative. This is denominator never negative, so we don't care about it. We divide by positive number and it doesn't change our sign. Does it make sense?
Oh, okay. Yeah.
And now we look at the sign of the denominator, or of the numerator, sorry. So to the right hand side from this critical point, let's say this critical point is x equals 1, okay? To the right hand side, we have point x equals 2. If we substitute x into this function, we can see that this is clearly greater than just 5, right?
Yeah.
And it's also with negative signs. So we're going to have numerator negative. Negative divided by positive gives us Yusuf,
oh,
Alan.
negative.
Great.
Yeah,
Great
but
job, guys.
it can't be negative though, the top one.
Huh?
The top one could never be negative either,
Why would you say so?
because let's say you plug in negative 1, you square it, you get 1 times 5, which is 5, and 5 subtract 5 is 0, and that works for every number.
No, if you substitute x for -2,
You get
it
4.
would be 4 times 5,
Oh,
you
yeah.
get 20.
You're right.
So you can say that it would never,
It's 0 or negative.
but it could be positive, and I can prove you. What if x less than 1?
Yeah, then it's a positive.
So you see, that's what we're gonna see when we look into x less than 1. When
Okay.
x less than 1 from on interval from basically from 1 to 0, it's going to increase. So from 0 to 1, it's increasing. And furthermore, from -1 to 1, it's increasing, isn't it?
1 to 1.
From -1 to
Oh.
1. If you take a look at the line, we have 2 points, 1 and -1. And now
Yeah.
let's take a look at the sign of the derivative to the left-hand side and right-hand side from each of these points. To the right-hand side from 1, we already discovered that it's going to be negative, right? It's going to decrease or be negative. What is between -1 and 1?
The sign.
Yeah, no, point. What is the coordinate between -1 and 1? That comes into your mind right away. We need to find the sign of the derivative on this interval. And it's going to be same, interval is going to have same sign between two critical points. Remember, sign of the derivative could change only after critical point. So it means that between 2 points, sign never changes. So to define the sign on the whole interval between 2 points, it's sufficient to find sign of the derivative in 1 point. So what point would I take between -1 and 1?
0.
Brilliant choice. So what would be if I substitute 0 into this function? What value would it take?
5. 5.
So
5 divided by.
So positive. I don't care what it's divided by. It's divided by positive number. That's what I care. Positive number divided by positive number gives me positive number, right? So I know that my derivative is positive from -1 to 1. Thus, my function is growing from -1 to 1.
Okay.
Make sense?
Yeah.
And my function is decreasing from 1 to the infinity. And my function is decreasing from -1 and to the infinity, right? From -1 to -infinity. Or from -infinity to -1 if I'm looking in positive direction. So my intervals are going to be from -infinity to -1, including or not including? Not including, because in point -1, derivative is equals to 0. This is the critical points when we change direction. They're not included into interval of decreasing or increasing of the function. Is it clear,
Yeah, it's clear.
Alan?
Yeah, it's good.
Can I clear it now?
Yep.
Perfect. So let's solve B real quick. So it's going to be f of x. We need to find f prime of x, right? X squared plus 4. And we need to find derivative of the following one. So first step, what I would do is to simplify it. Just write the square root in more convenient form for me as 1/2. And I need to find derivative of that. Is it clear? Alan, do you
Yeah.
understand why I'm writing this?
Yeah, because
Good.
we have to write it.
It's, yeah. So now I would find the derivative of the following one. But how?
Pardon me, what was the question again? Sorry.
Now I'm going to find the derivative of this. But how? What function? What rule should I use?
The quotient rule?
Yes, exactly. So, Alan, can you remind me how it looks like?
Yeah, I'm just gonna have to find the paper.
So I'm gonna go ahead and write it down. It's gonna be derivative of the outside function. In this case, it's 1/2, so I'm gonna bring it over as a coefficient, right? 1/2 and times what is inside the brackets, x squared plus 4 to the power -1, so -1/2, right?
Yeah.
Times derivative of what is inside, and inside I have x squared plus 4, which results in 2 times x.
I said the quotient rule, I meant the chain rule.
Yeah, it basically we use chain and coefficient rule as well.
Yeah.
Or no, coefficient rule is solely about fractions, right?
Power rule and chain rule.
Power rule and chain rule. True. So is this right? Is this how the chain rule looks like?
Yeah.
Is it correct? Guys,
Yeah, it's correct, I think.
so this is what we're gonna get if we apply
Yeah,
the
that's
chain
how
rule.
it is.
And now let's go ahead and simplify it, right? Open the brackets, all the stuff. Let's see what we're dealing with. And I have negative square root of x squared plus 4, right? Okay. So if it's negative square root, it means it's going to be in the denominator. Am I right? This is going to be 2, which is also in denominator, times x squared plus 4 to the power 1/2. Am I right? Oh, it's gonna be 2x in the denominator, right? Alan, Yusuf.
Yeah, it's gonna be 2x.
So this is what I'm getting as a result. So this is my equation of the derivative, and now I need to find for when it equals 0 and the denominator doesn't equal 0. So guys, can you give me a help? When does this derivative equal 0?
Okay. So it equals 0 at. So let me just check the bottom. The bottom will always be positive because it's squared the x.
I wouldn't.
Should I not assume that?
It's square root. Square
Oh.
root.
Okay,
Remember,
be
square root
positive
of
and negative.
derivative could be either positive or negative, right?
Yeah, okay, so it could be positive at. Is it
But remember, when does function equal 0?
at 0? With 2x?
No, yes, exactly. When nominator equals 0, when 2x equals 0, the whole equation gonna equal 0, right? Unless here we have 0. Am I correct?
Yeah.
But
Yeah,
if I substitute 2x equals 0 when x equals 0, it's simple, it's
Yeah.
straightforward. And I can say that this does not turns into 0 when x equals 0, right? Can you see
Yeah.
that?
yeah,
Because if I substitute 0 in here, I still gonna have positive number. Or am I? I'm gonna
yeah.
have
You will have a positive number. Yeah,
I'm gonna have square root of 4. And square root of 4 is 2, right?
yeah,
Oh, so x equals 0 at 2 as well? Or as at negative 2?
No. Because if you substitute negative 2, you would have 8 in root of 8.
Oh, so I completely ignored that.
So it's gonna be x equals 0, only solution when this function equals 0, right?
Yeah.
And now we found the x coordinate. Now we need to find the y coordinate. And to do that, we should substitute x into initial function. So f(x)(1) equals f(0), right? And f(0) is square root of 0 squared plus 4. Am I right?
Yeah.
Which results is square root of 4, which is 2.
I'm just copying it down, sorry.
Yeah. So the coordinates of our points, let's say answer, the point is A and its coordinates are 0 and 2, right?
yeah,
But I would like you to think, square root of 4, is it only 2 or is it also negative 2?
Negative 2.
Also negative 2, right? So basically, what we see here is that the modula of f of x equals 2, right?
yeah,
Because that's exactly what Square root is square root of number have positive modular, but it could be negative. So f of x could be -2, or f of x could be 2, right? You gotta check it out, because in this case it doesn't look logical to me, because we know that this function is in fact exists, right?
Yeah.
But it wouldn't exist if for the same value of x we had two values of function. Am I right? Remember the definition of a function from the first class. Function is such a set of numbers where for each one x exists one and only one y, right? Guys,
Yeah.
so square root of 4 is in fact 2, and it's gonna be 2 for any value of x. So if we look into this function, the square root function looks like this. Am I right? Guys,
Yeah.
so if it's gonna be same to the for the negative numbers, it's gonna be looking like this, right?
Hmm.
And we have critical points in 0. So we have cusp.
Okay. So can the
And-
answer is the answer also 0 -2 for the
Pardon?
point? Is the answer 0 and then plus or minus 2 for the point?
I don't understand your question.
Oh, here. Right here. Is this only 0 or is it plus or minus 2?
It's only +2.
Okay.
So this is coordinates on the initial function. So
Like,
it
oh,
means that it would be x equals 0, but y equals 2.
okay.
You see?
Yeah, I got it.
But derivative equals 0.
Yeah.
And you know that around this, if you look into the sign of the derivative, you would see that it's super growing here. If I'm right, it's super decreasing here. If you apply first derivative technique to this example, you would just substitute x for example, 1 and -1.
Yeah.
And you're gonna see the sign
Mhm.
that it's positive or negative to the left and right hand side of this point, which turned out to be a critical point, which also is a cusp on a curve. Is it clear now?
Yeah.
Can I clear the desk?
Yep.
Yeah.
Perfect. So now let's move on. And for each of the following graphs, I would like you guys to complete the 3 tasks. The intervals where the function is increasing, the intervals where function is decreasing, and the points where the tangent to the function is horizontal. So
Okay.
Yusuf, you're first.
Yeah.
Let's go and describe example A. So tell me where the function is increasing, at which intervals, state the intervals.
From -4 till I can see that the screen is really small.
This is better.
Yeah, it's a little bit better. Like from -4 here
Yeah.
till here. This is the increasing interval.
Okay.
And this is decreasing interval. This.
Okay.
And then this is increasing, the interval increases again. So it increases, decreases, and then it increases.
So can you state the intervals?
Like uh I'm not sure exactly how. Like
Why aren't you sure?
oh
Can you see the graph?
yeah, I can see it.
Can you see the points?
Yeah, I could see. So from -4 till this is 1. From -4 to 1.
This is -1.
Yeah. Oh no, yeah, sorry. From -4 till -1. That's increasing this here. And then from -1 till this is 2, right?
Yes.
Yeah, till 2. From -1 till 2, that's decreasing. And then from 2 till well, we don't know because the graph is going up, but it's going to be around 5, probably.
Yeah, so let's say this interval that they're giving to us is from 2 to 5,
2 to 5, yeah.
and 2 is not included,
Yeah,
as well as -1 is not included.
yeah.
Perfect. So what about third question? What are the points when the tangent is horizontal?
Uh,
What are the coordinates of such points?
what are the points when the tangent is horizontal?
Yes.
Um, I'm not sure exactly.
So what is
But
tangent? Tangent is derivative, right?
the derivative, yeah.
So tangent horizontal means derivative.
Yeah, so
He marked the points.
Means derivative equals 0. So horizontal tangent line
yeah,
will basically give us horizontal asymptotes on an interval for a function. Lines that this function is approaching but doesn't crosses them, right? Or
yeah.
local minima or local extrema.
Okay, so
Local minima or local maxima, or altogether it's called extrema. So
yeah, so find
basically, when
the
derivative
derivative.
equals 0, we have
Yeah,
horizontal tangent line, which also gives us horizontal asymptote. And basically, if you look on a graph, such point would describe function in such way that it either changes the sign after reaching this point, or we also know that there are examples when function is keep growing, right? After
yeah.
reaching this point. So on this graph, what example do you see? What example of horizontal tangent line? At which points do you see them?
You see them at the 4.
At,
Yeah.
yeah, graph A.
So the 4 and so here the 4 and the -1, and here is the this is here is this is 1 here, right? -1.
So let's say I have 2 points, right?
Yeah,
A and B. What are the
A and B.
coordinates of point A?
Point A is it's -1 4,
Mm-hmm.
and point B is 2, -1.
Exactly.
Yeah.
Beautiful. So here's the solution for the first one. Did you note it down,
I wrote it, yeah.
Alan?
Yep.
So, Alan, could you be so good job, Yusuf? Well,
Thank you.
Alan, could you solve the C for us?
Yeah. Can you go to it?
Yep.
Okay. So
Oh.
from
So E twice and E 3 times. E 1 time is function when interval when function is increasing. E 2 times when function is decreasing, or derivative of the function less than 0. Here's derivative of function is greater than 0, means increasing. And here derivative of function equals 0. So please go ahead, Alan, state those intervals.
can I tell you and you could write it?
Yep.
So for when it's increasing, it's negative infinity to -2. And it's also increasing at, oh, that's everything. That's it. And then for decreasing, it is -2 to 2. And then it's 2 to infinity for decreasing. And there is no point, which is a horizontal tangent. Or yeah,
So can you remind me definition of critical points?
critical points.
Yeah.
Well, I could tell you what they are. I can't define it though.
So definition of critical points is such point where derivative equals 0, or we also found critical points where derivative does not exist,
Yeah,
right?
so 0 or undefined.
On undefined or 0 or undefined, right?
Yeah.
So, and when the critical point function equals 0, we have horizontal tangent line, and when it's undefined, we have vertical tangent line, right?
Yeah.
That's why you add the round brackets, not the square bracket.
Yes, exactly. So here, basically, in this example, I can see that I don't have horizontal tangent lines. So I have only vertical tangent lines, and such lines are characterized by derivative is undefined, or I'm dividing by 0. Basically, you can understand it as this angle of a tangent line would be described as 0, right? And this angle of tangent line would be described as infinity. And it's strongly related to the tangent, to the definition of tangents, you know? Tangents is opposite, it's opposites, opposite side of the triangle, or if we have something like this, tangents would be this side divided by this side, or basically y divided by x. And y divided by x, that's exactly delta y divided by delta x, that's derivative, right? That's m, that's the slope of a tangent line. Am I right, guys?
Yeah.
So delta y over delta x is the slope of a tangent line. And this is also tangents of this corner, right?
Yeah.
Of this corner. And this corner, and tangents of this corner is y divided by delta by x, right?
Yeah.
So tangents of this corner also equals m. Am I right? If y divided by x equals m, then tangent equals m. because tangent is y divided by x. Makes sense?
Yeah.
So basically, this is the derivative as we defined it in limits theory, remember? We described m, slope of a tangent line to a curve at the point, as value of the derivative. And when m equals 0, it means that y divided by x equals 0, or y equals 0. So basically no gain, no race over run.
Okay.
So horizontal, that's why it's horizontal tangent line, because our function goes horizontally. It doesn't increases or decreases. Make sense?
Mhm.
Yeah.
That's why derivative equals 0, it's horizontal tangent line. But what would happen if y so big? So I'm getting literally 90-degree angle here. If I get 90-degree, tangent of a 90-degree angle equals infinity. And that's what's happening here. That's vertical tangent line. When function growing so fast over run of a function that the change of the y coordinate is infinitely fast, right? We're growing super fast, and that's exactly what's happening around this axis, around this vertical asymptote. Here, closer we get, the faster function begins to grow, and at some point it reaches infinite growth. Remember?
Yeah.
Yeah.
So now you're familiar with relation of tangent to the basically slope of a tangent line.
Yeah.
Can we move on?
Yes.
Yeah.
So let's look into D.
Okay.
So Alan, would you like to do it again, or Yusuf?
I'll try.
Okay.
Um.
So again, I, double I, and triple I.
So it's decreasing at in negative infinity to -1. I'll just wait for you to write that.
Increasing or decreasing?
Decreasing.
Decreasing. So it's double I.
Oh, wait, let me just do let me do the increasing first. Okay, so it's increasing from -1 to 2. And I'll wait for you to write it. And 3 till infinity. It's the square bracket for 3.
Why would you say so?
Because it's actually touching the point.
But it doesn't mean that function increasing or decreasing at this point. Remember? Whether function increasing or decreasing defined by the sign of a derivative at this point. And here I have cusp, clearly. It's sharp corner. Right?
So would it be a square bracket at 2 then? Because it's not a sharp corner.
But it's going to be a horizontal tangent line here.
Oh, yeah, you're right. And then it's decreasing at in negative infinity to -1.
Sorry.
It's decreasing at negative infinity to 1. To -1. Sorry.
Okay.
And
It's decreasing from negative infinity to -1.
yeah. And it is also decreasing at 2 to 3. And there are the horizontal tangents at point -1 and 0.
I wouldn't agree with you because remember, cusps are occurring when derivative is undefined. So
Oh
when
yeah.
derivative is undefined, we're either getting vertical asymptote or cusp.
Okay, so then it's only at 2 and 3.
Exactly. Not only at 2, because at 3 it's cusp again.
Well, 2 and 3, like the 0.23.
Oh yes, that's good. That's good to note. So
Okay,
2
so
for
cusp.
A, 2, 3. That's it?
Yep.
Perfect. Do you need this? Did you
No.
copy it?
I got it down.
Perfect. So I believe you can deal with this graph by yourself, right?
Yeah.
Can you tell me, is there any cusp on this graph?
No.
No.
Oh wait, there is, I think. Oh no.
Is that it? Or
Actually, there is a point where
This one.
here we're
Yeah.
gonna have a little problem because you see, it's not like smooth curve.
Yeah.
So it means that derivative from left-hand side and from right-hand side from this point is going to jump, right? It won't approach the same value. So derivative would not exist at this point.
That's a cusp.
Yes.
Okay. When I look at it first, I didn't see it.
So derivative does not exist also means it's a cusp. Or vertical asymptotes. How you define whether it's vertical asymptote or cusp? If it's going to be a vertical asymptote, function would not exist at this point, right? And also, because you see, function tries to reach this vertical asymptote, but it never crosses it. And another thing you need to see that sign of the derivative, the value of the derivative is either negative infinity or positive infinity to the left and right hand side. Then it's going to be vertical asymptote, as you can see on this graph, right? Here, from both sides, derivative is going to be positive infinity. Am I right? Guys,
Yeah.
here is going to be negative infinity. Here's positive infinity and negative infinity.
Yep.
No. Here it's not negative infinity in the last one. Here it's
Positive infinity.
no. It's gonna be horizontal asymptote as they draw it. Yeah, we expect it looks like they want us to think like it's going to go like this,
Okay.
right? Never reach x again. But we don't know. At
Oh,
this point, derivative is neither 0, neither infinity, it's just some negative derivative because it's decreasing, right?
okay.
So let's move on to the next slide. And here's basically critical points and local maxima. Please verify whether what you memorized corresponds with this notation, that we're gonna have local critical point that defines as like certain coefficient at which derivative equals 0. This is basically local minima and local maxima points, sorry. Not critical point, but local minima or local maxima.
Uh-huh.
The local minima and local maxima are also type of critical points. Is it clear?
Yeah.
As well as points that are causing the vertical or horizontal asymptotes. Basically, minima and maxima are part of horizontal asymptote, isn't it?
Yeah,
Because you see, minima and maxima points are the point where function changes sign, thus derivative equals 0. Thus, it's a horizontal asymptote. So let's do a few more exercises. Here, Yusuf,
yeah.
could you be so kind and explain what it means to determine the critical points of the graph of a given function?
So, so explain what it means to determine the critical points of the graph of given function,
Exactly.
and the function is for a, right? Equals x.
In this question, they ask for arbitrary function. For in general case, what is your set of actions in order to determine a critical point?
So first
Sorry, Yusuf.
Yeah.
Concentrate and look here. This is what we just concluded, that basically we're looking into critical point,
yeah,
and such critical point would be described by the value of the derivative,
Yeah.
0, undefined, right?
okay, so like
Or in okay.
to find the critical points of the function, we first have to take its derivative with respect to x, right? And then set the derivative to equal or equal 0 or undefined, right? And this will give us the values of x where the slope of the tangent line to the graph. Is that how to find, or
Yes, exactly. So these values of x are going to give us points when the tangent line to the curve of a graph at the point would be either horizontal,
or vertical? Yeah,
or vertical, yeah.
yeah,
And basically vertical, it's not a tangent line, because vertical asymptote, a tangent line, first of all, is such line that has that shares one point with the curve. Is it correct?
yeah,
And asymptotes are such lines that are never being crossed by the curve. Am I correct?
Yes.
Asymptotes are such lines that the curve approaching but not crossing.
Yep.
So once we define so derivative equals 0, this would be critical points that are giving us horizontal tangent line,
yeah.
and derivative undefined would give us vertical asymptotes. Is it correct?
Yeah.
So, okay, Yusuf, what would you do for function A? Explain, how would you find the critical points?
For a,
Yeah, yes.
so first, um, wait, so first is find the derivative of it, right? Then we can
Yusuf?
yeah,
So yeah, you're right. You need to find the derivative, because critical points are going to be such points where derivative takes specific values, right?
yeah,
So in order to find those points, we need to find the derivative. So once we found the derivative, we'll look whether this derivative could be equal to 0 or could be undefined.
yeah.
So go on, please.
Uh, 1 second.
For this particular case, if you find the derivative of this function, how it would look like?
To find the derivative, we can.
So
we-
here,
we
simple
set it to zero.
difference of a terms, right?
Yeah, so setting the derivative to equal to 0,
So what is the derivative?
uh, it would be 3x squared minus 12x equals 0.
Don't hurry up. Just the equation of the derivative. You said it right. But don't stick in it equals 0 just yet. Once
Oh,
you
okay.
got the equation of derivative, you gotta
Yeah.
look whether it could be equal 0 or it could be undefined, right?
Yeah,
Because, for example, if I had uh, x squared here, and plus here, this never equals 0 because it's always positive number, right?
yeah,
So there is no point in searching for those points when it equals 0. But in my case, I have something squared, subtract something. So there are points when this equals 0.
yeah.
And another thing, what if I had factor here divided by x? I would
Yeah, so
find that x equals 0 would be undefined for me.
oh, okay, yeah,
Is it clear?
yeah,
Perfect. But in this case, I have nothing like that.
yeah. And then we can factorize the 3x 3x squared minus 12x equals 0. We factorize it and we get 3x 3x to x minus 4 equals 0. And then this equation is true when, like we can say this equation is true when x equals 0 or x equals 4. These are the critical points of the function.
Perfect. So in this points, what is going to happen to the graph?
What's going to happen to the graph?
Yeah.
Like as x the graph will have like a hill shape when with the peak of like x equals 0.
Exactly.
Yeah,
So basically, if it's going to be peak, it's going to be local maxima or local minima, or in other words, it's going to be point where derivative or where function changes direction or derivative changes sign. So if I go ahead and plot these 2 points on my coordinate system, it's going to be x equals 0 and x equals 4, right?
Yeah.
So there's going to be 2 points where my derivative equals 0. Now I should go ahead and basically B asks me to sketch the graph, right?
Yeah,
And to sketch such graph, I'm going to go ahead and find the value of y at this point. y1 would be equal to 0 and y2 would be equal to 16 times 4 is 64. Subtract. Yusuf, help me. 64 subtract
64 subtract
6
4.
times 16 or 96, right?
Yeah,
So I'm gonna get a negative number, which is
which is
negative.
negative 32.
Yeah, I think it's just about right. Negative 32. All right. So it's gonna be value of y here, way below, right? Negative 32. So now I have my 2 points when x equals 4 and x equals 0, right? This
Yeah,
point is 0, 0. So I know that my derivative changes sign, and now I'm gonna look into sign to the left and right from this point.
yeah,
So from between before 0, I have -1. In the point -1, I'm gonna have. Now I'm gonna look into derivative. I'm gonna use my cool technique where it's called first derivative test. I know the derivative. Now I substitute -1 in here. I substitute
yeah.
-1 and I see that it's gonna be positive number. It's gonna be 3 plus 12. It's gonna be 15, right?
Yeah.
So to the left, my function from this point is growing. So coming something like this. Between 0 and 4, I have point which is 2, for example. And if I substitute 2 in here, it's going to be 4 times 3, which is 12. 12 subtract 24 is -12, right? So my function is decreasing here. Am I correct?
Yeah.
And to the right-hand side from 4, I'm going to have 0.5, for example, and I'm going to have 5 squared, which is 25 times 3, which is 75, right? 75 subtract 60. Positive. So I know my function is going to grow. Am I right?
Yeah.
So if I want to be exactly precise, I would just find one more point at each side of this intervals, right? For x equals 2, I would find the y point coordinate. And I already know that my function is decreasing. So I would draw a nice smooth curve that going into this point reaches this horizontal tangent line, changes direction and increasing again.
Yeah.
And before 0, my function is going to act like something like this, right? It's going to grow up to this point. Am I correct?
Yeah.
So here it is. We plotted this graph of this function. And note, this is polynomial function of third power, right? Polynomial function of second power is parabola. It has one vertex. Am I correct? It has only one solution when it equals 0.
Okay. Yeah.
When derivative equals 0.
Derivative equals 0. Yeah.
But here, we basically have it polynomial function of third power. So we have thus 2 points when derivative equals 0. And you can go ahead and take a look at if it would be greater powers. Most likely, you're gonna get more numbers of solutions. But today, we covered our portion of problems for unit 4.1 and 4.2, right? Critical points, local extrema,
Yeah.
horizontal and vertical asymptotes. And I'm really grateful for you guys for participation, and I hope you liked today's class. And that's it for today. I hope you have a good rest and have a beautiful week.
Really good class. Thank you.
Thank you.
Thank you so much. Have a good afternoon, guys.
Have a good day. Bye. Thank you.